Hello, in this video we will talk about list type. List is a collection of elements of the same type. So how will we define list type in Haskell? We can write that data type list of type A is either nil or cons with two values, A and list A. Element of type A is a head and element of list A is tail. This can be translated to Scala in the following way. We define seal trait list of type A with two children, object nil and case class cons with head of type A and tail of type list A. This can be translated to Java in the following way. We define interface list of A with two children, class nil of A and class cons of A. Well, there are some small differences between these definitions, for example regarding with covariance and subtyping and so on, but we will ignore such small details here. Okay, let's define list type as in type theory. So type formation rule states that if A is a type in context gamma, then list of A is a type in the same context. Well, it means that for any type A, list A is a new type. So we can say that list is a type family. Next rule is constructing rule. In every context gamma, if A is a type, then nil is a value of list A, and if H is element of type A, head, and T is element of type list A in the same context, tail, then cons HT is element of list A in the same context. Next rule, eliminating rule, which is used for pattern matching. If C1 is element of type C and C2 is element of type C and C2 depends on elements H and T of types A and list A correspondingly, then we can make pattern matching of on element X of type list A, whether it is nil or cons. Cons with head H and tail T. So if X is nil, we return C1. If X is cons with head H and tail T, then we return C2 of HT. Next rule is computation rule, which describes what happens if we apply constructors firstly and then eliminator. Well, surely if we apply eliminator to nil, then we have first argument. If we apply eliminator to cons with head H prime and tail T prime, then we have second argument with H prime and T prime substituted instead of head and tail. And there is no necessity in uniqueness principle for list type. Okay, let's look at some code. So we define variable A, type variable A. Then we say that list of A, which will be printed list of A, is a type, and we define list of A as an inductive type with constructor nil, which returns a value of this type list A, and constructor cons, which takes head, tail, and returns the whole list. We will denote nil as nil and cons as cons. Well, it's obvious that list type is an inductive type, because to define value of the whole list you need to have its tail defined already as a list. We define some variables, and let's define function of finding size of a list. Well, size of a list is a function which maps list to natural number, and we will make pattern matching on its argument of type list A, whether it's nil or cons with head A of type A and tail AS of type list A. AS is plural of A. Okay, so if our list is nil, then size is 0, and what size of our list will be if size of tail is n? Well, obviously it will be suc n. Let's check our definition. Let's feed it to REPL. I've already started REPL with a command sbtmantle test console. Okay, let's define several variables of type A. We already have A, let it be A1, and A2. Let's have some list. For example, list with elements A, A1, A2. Then it will have head A and tail list with head A1 and tail list with head A2 and tail nil. Okay, so size of list, well, it should be 3. Let's make it fancy. Yes, it's 3. So everything works. Thank you for watching. Now you are ready to solve some problems with list. For example, implementing functions of head, tail, checking if list is nil, and so on. Thank you, and see you in the next video.